There are several methods for predicting slopes and deflections for beams, one of which is double integration. An advantage to this method is that it gives an equation for slope and an equation for deflection everywhere in a beam, unlike the other methods which will tell you information about a single point. The key concepts we're going to use are generating equations for moment along a beam and generating equations for deflection along a beam using the double integration method. Here's our beam. It is simply supported, pin at A, roller at B, with a cantilevered end and a couple moment applied only at end C. We're going to use double integration to predict the vertical deflection at C. And note that the modulus of elasticity, E, and the moment of inertia, I, are constant along the beam. And here's the approach we're going to follow. First, we'll approximate the answer. So that we have something to compare to after our calculations. And we're going to calculate reactions. From there we'll calculate the moment equations. And we'll integrate the moment equations divided by EI to get slope everywhere. And we'll integrate the slope equations to get vertical deflection. And because those are indefinite integrals, we're going to have constants of integration. We'll find those constant values. Then we'll be able to predict the vertical deflection at C. And we'll come back and compare with the approximation to make sure that we have a reasonable answer. Step 1, let's approximate the answer. If we look at the deflected shape of this beam, we expect it to be something like that. Well, we can approximate this situation and look at just the cantilevered end with the couple moment, and we get a downward deflection as such. Now, since the region from A to B can deflect, that means we get a rotation at B. So this vertical deflection we expect to be larger than this, but this will put us into the ballpark. And so let's predict the vertical deflection for this situation. It will be an underestimate, but I picked this geometry because it's represented in the front cover of our textbook as the following situation. So we have a way to calculate the peak deflection of a cantilever with a couple moment at the end by using this formula, which, by the way, was derived using double integration or one of the other methods for predicting deflections of beams. So our underestimate of the vertical deflection at C is a minus m naught L squared over 2EI. And it's minus because the figure in the front cover of our textbook has a counterclockwise moment. We instead have a clockwise moment, which means our deflection, which is measured positive as up, is predicted to be down. We'll have a negative times the applied couple moment, the distance, or length rather, of our cantilever over 2EI, and that quantity is a minus 900 kilonewton meter squared over EI. So we know our answer has to be larger than this, but we wouldn't expect it to be an order of magnitude larger. Now let's calculate reactions. Because we'll need those in order to construct our equations for moment. We'll have a vertical reaction AY, vertical reaction BY, and a horizontal reaction AX. Let's sum moments about point B. I can choose the direction to be positive, so I'll choose clockwise as positive, because then my unknown vertical reaction at A contributes a positive moment, and my applied couple moment is also positive. Solve for my unknown vertical reaction at A. We have a minus 8.33 kilonewtons. We'd assumed it was up. It's not. It's in the other direction. Now we'll sum forces in the vertical direction. We'll choose up to be positive for our summation. We have the contribution of the negative reaction at A. Add in the reaction at B. BY is a positive 8.33 kilonewtons. So it is in the direction we drew it, up. Now we're ready for step 3, the moment equations. We'll need a new equation after each reaction, concentrated force, start or stop of distributed load, or applied couple moment. So in the case of this problem, we're going to need two equations for this structure. We'll have an equation in the range of x1, which will run from A to B, and we'll have an equation in terms of x2, which will run from B to C. So let's cut it between A and B. I have a free body diagram cut within the range of x1. We have the negative reaction at A, the unknown shear, which is a function of position, and the unknown moment, which is a function of position. So we sum moments about the cut. We'll choose counterclockwise this time as positive. We get a negative rotation, but it's a negative quantity from the reaction through a distance of x1, and our unknown moment at the cut is counterclockwise, so it's positive contribution. We solve that, and our equation for moment in the range of x1 is a negative 8.33 kilonewtons times x1. Now let's cut it somewhere between B and C. We have the reaction at A the reaction at B, the unknown shear within the range of x2, the unknown moment as a function of x2. Distance between A and B is 6 meters, and our overall length is x2. We'll sum moments about the cut. Again, we'll choose counterclockwise as positive. Get a negative contribution, but a negative magnitude from the reaction at A through a distance of x2. We get a negative contribution from the reaction at B through a distance of x2 minus 6 meters. And we get a positive contribution from the moment in the range of x2. Solve for the moment at x2, and we get all of the terms with an x2 in it cancel out, so all we get is minus 50 kilonewton meters. So our moment equation is a constant, a flat line. Now we're ready for step 4, which is to integrate the moment equations divided by EI, and that will give us slope. The rotation at any point, theta, is the same as the slope at any point, because we're limiting our prediction abilities to relatively small deflections, small angles, and that's a reasonable limitation. So slope is also often referred to as the theta, and that's the integral of m over EI dx. So specifically from A to B, which is our range for x1, our slope is going to be the integral of minus 8.33 kilonewton times x1 divided by the constant EI dx1. Well, we're integrating a polynomial, so we increase the power of the x term squared and then divide the whole thing by the new power. So we have a minus 8.33 kilonewton x1 squared over 2EI plus our constant of integration, since this is an indefinite integral, and that simplifies to minus 4.17 kilonewton times x1 squared over EI plus the constant of integration. And we're going to call that equation 1. Now, from B to C, we'll get an equation for the slope, and we'll call that theta 2. This is the range of x2. We'll integrate the equation we got for moment, which was a constant, divided by the constant EI with respect to x2, which will give us a minus 50 kilonewton meter times x1 divided by the constant EI plus a new constant of integration. We'll call this one equation 2. We have two constants of integration that we'll need to find in order to have equations that we can use for predicting slope or deflection anywhere along the beam. But we'll have to wait to find those until after we generate our equations of vertical deflection. Now we're ready for step 5, where we integrate the slope to get vertical deformation. And so the basic idea looks like this. So from points A to B, the equation for vertical deformation will be the integral of a minus 4.17 kilonewton over EI times x1 squared plus the first constant of integration, dx1, and just a reminder, x1 is measured this way. We're integrating polynomial with two terms, one of them being the constant. So we'll raise the power of this term, x cubed, and we'll divide it by that new power. So we get a minus 4.17 kilonewton over 3ei x1 cubed. We integrate this constant with respect to x1, and since the power on this x is 1, we divide c1 by 1, we just get c1, but we get a new constant of integration, and if we simplify this a little bit, we get a minus 1.39 kilonewtons over EI x1 cubed plus c1 x1 plus c3. And we'll call this equation 3. Then from B to C, which is our region of variable x2, our equation for vertical deflection in that region will be the integral of the minus 50 kilonewton meter over EI times x2 plus the constant c2, all with respect to x2. So we'll raise this to the second power and divide by 2. Times x2 squared. We'll multiply that by x2, and we need a new constant of integration, c4. We'll simplify the first term, minus 25 kilonewton meter over EI x2 squared c2 x2 plus c4, and we'll call this equation 4. So we now have the 4 equations for slope and deflection across the entire beam, but we also have 4 unknown constants of integration. So step 6 is to find the constants. To do that, we'll use boundary conditions. And our boundary conditions include, at x1 equals 0, remember this is x1, and this is x2. At x1 equals 0, the vertical deflection is 0 because it's pin support. At x1 equals 6 meters, the vertical deflection is 0 because it's a roller support. At x2 equals 0, well, we're right back at that same point B, but it's a new equation. It's vertical deflection in terms of unknown x2, or not unknown, but variable x2. That gives us 3 pieces of information, but we have 4 unknown constants, so we also need a continuity condition. And that comes where x1 and x2 meet up at point B. So at x1 equals 6 meters, x2 equals 0 meters, and we have that the slope calculated in the region of x1 has to equal the slope in region x2 because we're at the same point. Now let's use that information. We're going to substitute the boundary condition at x1 equals 0 into equation 3, which we had found was the vertical deflection in the range of x1. So we have the vertical deflection is 0. It equals the minus 1.39 kilonewtons over EI times x1, which is 0, cubed, plus the constant C1 times x1, which is 0, plus the constant C3. So everything is multiplied by 0 except C3, so my constant C3 is 0. Now let's substitute the other end, x1 equals 6 meters, into that same equation, equation 3. Plus we'll use our knowledge of the constant C3. So 0 equals minus 1.39 kilonewtons over EI, 6 meters cubed, plus the constant C1 times 6 meters, plus the constant C3, which is 0. Solve that for C1, and we get a positive 50 kilonewton meter squared over EI. Now let's use our continuity condition along with our knowledge of constant C1. So we'll substitute x1 equals 6 meters into equation 1 and x2 equals 0 meters into equation 2. Looking back, here we have equation 1 and equation 2. We already know constant 1, so we'll find constant 2. So we have minus 4.17 kilonewtons over EI times the 6 meters squared plus the constant of C1, which you just found to be 50 kilonewton meters squared over EI, and that is equal to the minus 50 kilonewton meter over EI times x2, which is 0, plus the constant C2. We solve that, find that C2 is a minus 100 kilonewton meter squared over EI. We now have one more constant to find, C4. So let's use our last boundary condition, and we'll substitute x2 equals 0 into equation 4, along with the constant C2 that we already have. We found this to be equation 4. Since the deflection at that point is 0, we have 0 equals a minus 25 kilonewton meter over I, x2 is 0 squared, minus constant C2, a minus 100 kilonewton meter squared, over EI times x2, but that's 0, plus constant C4. Well, all the other terms drop out. C4 must equal 0. We're now ready for step 7, which is to predict the vertical displacement at C using equation 4 with its constants determined. So we ultimately discovered that the vertical deflection in the range of x2, which runs from B to C, is given by minus 25 kilonewton meters over EI times x2 squared minus 100 kilonewton meters squared over EI times x2. So for the vertical deflection at C, we're talking about at x2 equals 6 meters. The vertical deflection at C is a minus 25 kilonewton meter over EI times 6 meters squared minus 100 kilonewton meters squared over EI times 6 meters, and we get a negative 1500 kilonewton meter cubed over EI. And remember that a positive answer would have been a vertical, or it would have been an upward deflection. We had originally predicted or sketched out that our deflection would be as such. So we expected it to be negative. Now step 8. Compare with the approximation. And we had found the approximate value to be negative 900 kilonewton meter cubed over EI. And since our prediction is a negative 1500 kilonewton meter cubed over EI, we knew this had to be an underestimate. It is smaller, but they're in the same order of magnitude, so we'll say that checks out. We have reasonable confidence that this is a valid prediction of the deflection or anticipated deflection at point C. Now let's go back and review. We started by looking at the predicted deflected shape and recognizing that the cantilevered end is similar to a situation we can look up from the front cover of our textbook, a cantilevered beam with a couple moment applied at the end. And there's a formula for peak deflection, or deflection at the end, for that situation. We use that approximation for the real situation to come up with an underestimate, or a lower bound, on what the deflection would be, but it also gives us an order of magnitude to compare against at the end of our calculations. We then calculated the reactions so that we could calculate the moment equations. And since there is a support at B internal to the beam, we need two equations to describe moment along the length of the beam, which means we also need two equations to describe slope along the beam and two equations to describe vertical deflection along the beam. We then integrated those two equations of moment to get the two equations of slope. Don't forget, you need to divide the moment by EI before you integrate. We then integrated the two equations of slope to get the two equations of vertical deflection, but because those were all indefinite integrals, we also had four unknown constants to deal with. So we used three boundary conditions and one continuity condition in order to find each of those constants. Once we did, we had an equation for vertical deflection in the range of x2 that we could use to predict the deflection at point C. And then when we compare it with our approximation, we find that our predicted value using double integration is larger than our approximation, but not double. And so we're at the same order of magnitude, and we meet the criterion that VC has to be bigger than the approximation. So we think we have